right? So I told conductivity of a solution of electrolyte is called electrolytic solution conductance, correct? Conductivity of an electrolyte solution is called electrolytic conductance. It is caused by a movement of ions. Please know Na plus Cl minus ion. So it is caused by a movement of ions. They are generally caused by a movement of ions. Ions are the critical thing here. Earlier in the metallic conductance, it was electron which was the current carrier. Here the ions are the current carrier. Correct. So it is caused by the movement of ions within the solution of electrolyte under the influence of applied electric potential difference. For example, if you add a battery, there is a potential difference between these two. It's a potential difference between these two, right? Because they are connected now. And with this, the ions will carry current. Correct. As I already told, conductance is inversely proportional to resistance. So I can say here also electrolytic conductance will also be nothing but G will be nothing but 1 by electrolytic resistance, that is R. Correct. So Ohm's law is true here also. Ohm's law is true here also, which we have studied in physics. So we know that V is equal to IR, right? The Ohm's law. This is nothing but the electric potential difference in volt. Since we are using in chemistry E instead of volt, we will use E term. E is equal to IR. Or let me be E is equal to IR, because we use electric potential is IR, right? Where I is the current and R is the resistance. Right? Here if you want to find the resistance, again I told R is nothing but rho L by the same formula. Rho is resistivity, L is the length, A is area. So this L is what? L is the distance between two parallel plates. This is the L. And what is A? A is the nothing but area of cross section of the solution which is in contact with electrode. So this one is my A, the one which I have. Because only this much area of the electrode is in contact with the solution. This is my A. Correct? So it is not the area of the whole, please note the A is not the area of the whole electrode. A is the area of only the electrode that is in contact with the solution. And rho we know that is nothing but specific resistance or resistivity. Right? And please note, for any cell, if you have constructed this, L by A will be constant, right? Because the length between these two electrodes will be constant. And this area will also be constant because it will have fixed volume of solution. So this L by A, since it is a constant value L by A, and this constant for a cell, it is also called cell constant. Why? Because length and area is constant for a given cell, right? So L by A will be constant for a given cell. It's also called cell constant. Correct? So the other formula which we studied was kappa is equal to 1 by rho. This is also true here also. Correct? Please note, if you see the pure water, it will have very, very low conductivity. The bulb may not glow also, but if we dissolve the electrolytes in this, for example NaCl, the bulb will glow. The conductivity increases. So in this case, the conductivity depends on what? The nature of electrolytes. Obviously, if you see, if you add NaCl, the bulb glows more. If you add weak electrolyte, for example acetic acid, the bulb glows less, right? So I can say that the conductivity here also depends on one, the nature of electrolytes that we have seen. The next is the size of ions produced. Why? Because here the ions are the carrier, right? So if I have Na plus ion or I have CH3CO minus ion, there is a difference in the size. So size of ions produced is something which is critical. Also, the nature of solvent. Why? I'll tell you the nature of solvent. Because if the solvent is very viscous, it is very thick, it will obstruct the flow of ions, right? So viscosity of solvent also plays a role. Fourth, increase in temperature. Please note here, it's a little different scenario here. So if we increase the temperature what happens? The mobility of ions also increases, right? Because see, here the ions are the carrier. You see, the one which was moving in the last slide, right? The red dots which were jumping in here, there, they are the carriers. The mobility of the ions also increase, and the mobility of the cations also increase, right? All the ions, they increase. Since the mobility of the ions increase, the conductivity also increase. That is one part. Second part, if you increase the temperature, the viscosity of solution decrease. Since the viscosity of solution decrease, the ions can move around easily, and thus conductivity also increase. Correct? So it depends on nature of electrolyte, size of ions, nature of solvent, all. And for the temperature, there's a different ball game here. In the case of metal conductance, the metal conductance is because of electrons. So if you increase the temperature, see, in both cases, the moment you increase the temperature, the atoms move around here and there, right? Here we have ions, so they move around here and there. But since in the case of metal, the atoms move around here and there, it is difficult for electrons to pass through. So the moment you heat a metal, the conductivity decreases. But in case of this scenario, the moment you increase the temperature, the ions move around here and there. And here the temperature, the conductance is because of ions only, and thus the conductivity increases. Let's do a recap of what we have studied about the metallic conductance and the electrolytic conductance. So as I told, in metallic conductance, my electrons are the carrier of current. So in this electrolytic conductance, my ions are the carrier of current, right? The metallic conductance happens in metal under the influence of electric potential difference, obviously, and this happens in electrolytes under the again influence of electric potential difference. Here the conductivity decreases with increase in temperature. I have showed you why the conductivity decreases with increase in temperature, because the atoms here moves around. In both cases, when you increase temperature, right, implies atoms or ions, they move around at higher speed. Correct. Now, but in this case, the moment atoms move around at a higher speed, since the carrier is electron, for electron it is difficult to pass through this high speed moving atoms or ions. But in this case, the moment you heat the temperature, the atoms or the ions move. Here we have ions only. Sometimes we have atoms also, because for weak electrolyte, if you see, not all the atoms break into ions, right? So the atoms and ions, they move around at a high speed. But here the carrier is atoms and ion itself. The ions itself are the carrier, right? So since the carrier itself, the current carrier is the ions itself. So as we increase the temperature, the conductivity increases. Okay. So they generally have high conductivity, very, very high conductivity. Electrolytes generally have very low conductivity. And the moment if you use a metal for passing electricity for a long time, you won't see any difference in the metal. Metal will be the same. But if you use electrolytes for passing electricity for a long time, you'll see there is a change in the electrolytes concentration, especially if you used DC current. Right? The electrolytes concentration may change. This is something we'll see in the next few slides. Also, if you see the Nernst equation also implies the same thing. For a cell, the concentration change over a period of time. And here also, since the same electrolyte is used for a long time, the concentration will change. And the resistance in this case is due to vibrating nuclei, the vibrating atoms here. And here, because it is electron which has to pass through these vibrating nuclei. But in this case, the resistance is due to ionic attraction, viscosity of the solvent, and solvation of the solids. Resistance is because of some another reason, right? Because the main difference is this is electron, this is the ions itself. So that is the difference between the metallic conduction and electrolytic conduction. So we have seen a lot of new terms: resistance, resistivity, conductance, conductivity, right? So let's do a recap of all the SI units, because these are little critical for us, right? So we have seen that resistance is rho L by A. That is one formula we have given, right? So let's talk about resistance first. Denoted by R, and SI unit is ohm, correct? And ohm is nothing but kg meter square per second cube A square. We don't need this formula anyway. So SI unit is ohm, just focus on that. And the formula is R is equal to rho L by A. The next is opposite of resistance, that is conductance. Denoted by G, that is nothing but 1 by R. And if you put the same formula, this becomes AL by rho. Correct? So SI unit for this is Siemens, SIEMENS, denoted by S. Here we have ohms, here we have Siemens, right? This Siemens is nothing but per ohm, also called mho, right? This is what it is, because conductance is nothing but 1 by resistance. Third, we have resistivity, something but rho, this value rho. This is also called specific resistance, right? And this SI unit is ohm meter. We have seen that. Why? Because this is L by A is nothing but 1 by meter. So you put this side, so this rho becomes R into, if you see, rho becomes RA by L, right? Find the unit. Resistance is ohm, A is meter square, and length is meter. This gets cancelled. This becomes rho meter. So SI unit is rho meter, right? And rho centimeter is also used. So 1 rho meter is nothing one rho meter is nothing but 100 rho centimeter. So both are used actually, but rho meter is the SI unit. So opposite of resistivity is nothing but conductivity. Is nothing but kappa, and nothing but 1 by rho, right? So its SI unit is Siemens per meter. Similar to this, we have rho meter here. This is Siemens per meter, correct? So conductivity of a material is its conductance when it is 1 meter long and its cross section is 1 meter square. Correct? So if you want to see the relation bit similar to here, we have 100 Siemens per meter is nothing but 1 Siemens per centimeter. You can do the math and see why it is, right? So that is all about the 4 different terms we have seen: resistance, conductance, resistivity, conductivity, and the SI units for these terms, because these are essential to solve numericals. These are the common ones. If you see the conductors, sodium, copper, silver, gold, this is the conductivity. If you talk about the insulator, conductivity is pretty less. If you talk about the aqueous solution, conductivity is there, but if you see the units, this is 10 to the power 3. This is nothing, right? So compare these two, they have very, very high conductivity. Also, if you see the conductivity of the solution depends on the molarity. For example, in both cases you have HAC is the aqueous solution, but the molarity is different, the concentration is different, and they have different conductivity. Semiconductor, we have CO, silicon, germanium. So we won't study much about semiconductor. We have studied this in the last chapter itself. And glass and all, if you see, the conductivity is pretty bad and they are called insulators. Almost they don't conduct electricity. Right? They told the unit of conductivity is